This water is 4.5 billion years old. I can see you're looking all confused there. Let me explain. The origin of Earth's water is one question, but where did water come from is another. And in this video, we're going to dive into the wonderful world of how water was formed and where it came from. In a brand new research article called We Drink Good 4.5 Billion Year Old Water, what a title, it shows that young solar systems have abundant water in them. And in solar systems like ours, water is along for the ride as stars and planets form. And the evidence is in heavy water. And it shows that nearly half of Earth's water is older than the planet itself. And you're probably wondering what heavy water is? Well, we'll come on to that. But first, let's take a step back in time. It all starts off with our solar system, which was once a giant molecular cloud. The cloud is mostly hydrogen, water's main component. Next are helium, oxygen, and carbon in abundance. But the cloud also contains tiny grains of silicate dust and carbonaceous dust. And out here, in this cloud, it's extremely cold. And when oxygen encounters grains of silicate dust, it freezes and adheres to the surface. But water isn't water until hydrogen combines with oxygen. And it's only once the dust, which is covered in frozen oxygen, comes in contact with a hydrogen particle that it mixes together and creates water. But in this case, it doesn't create the liquid form of water. No, it actually forms two types of water ice. We have regular water and we have heavy water. Now, heavy water contains a heavy hydrogen atom known as deuterium. It has one proton and one neutron in its nucleus. That's what separates it from regular hydrogen, also called protium. Protium has one proton, but no neutron. Both these hydrogen isotopes are stable and exist today, and both can combine to create water. Now, coming back to that dust cloud. Gravity begins to exert itself in this environment, creating clumps of matter in the center. As more mass falls to the center of this molecular cloud, it starts forming a protostar. During this process, heat is generated, causing gas and dust in the disk to rise to 100 Kelvin. Now, out there in the cosmos, 100 Kelvin was quite high. On Earth, however, well, it's bitterly cold, nearly negative 173 Celsius. But chemically, it's enough to trigger the process of sublimation. This is where ice changes into water vapor. This process of sublimation requires heat, which therefore means it has to occur near the heat envelope around the center of this cloud, also known as a hot coronal. At this point, water is abundant, though it's all in vapor. And a typical hot coronal contains nearly 10,000 times more water than there is on Earth today. As time passes and the clumps of matter get bigger and bigger and the protostar gets bigger, it starts to rotate. This then causes the surrounding dusts and grains to start to create a flat disk. This is what's known as a protoplanetary disk. And it contains everything that will eventually become our solar system. Now, next is the important part. Even though the newly created star is generating heat, it's not that much heat, which means that there is a temperature gradient from the center of the cloud to the far reaches of the disk, therefore getting colder and colder. Now, coming back to the water ice that was created at the start. During the process of sublimation, it obviously turns to gas, but as that gas moves further and further away from the center of the disk, it condenses again on the silicate grains that exist. This creates an icy mantle around the dust. But now the water molecules hold a history of water from the solar system. Thus, the dust grains are the guardians of water inheritance. Now, as time passes and the solar system begins to take shape, it resembles a more fully formed system. Planets, asteroids, and comets start forming and taking orbits. Now, you're probably wondering, how do we know then that the water that I just drank out of this glass is 4.5 billion years old? Well, it all comes down to the ratios of heavy water and regular water. You see, deuterium, which we spoke of earlier, which creates heavy water, is only formed in the initial stages of the Big Bang of the universe. However, not much of it actually formed. Only one deuterium for every 100,000 protiums, or, regular hydrogen. That means if deuterium was evenly mixed and distributed across the entire solar system, the abundance of heavy water would be somewhere between 10 to the minus 5. And that ratio would also be evident on Earth. But that's not what we see. The Earth actually has 10 times more deuterium than it should. This means something must have occurred to enrich it. And for that, we have to go back to the hot coronal region, which we spoke about earlier as the cloud started to clump together, creating a protostar. See, during the initial process of the oxygen going onto the dust and then mixing with hydrogen to create the icy water, that icy water process actually attracts more deuterium than it does regular hydrogen atoms, therefore creating a concentration of heavy water. Therefore, abundant heavy water means that there was a molecular cloud clumping event, which was the birth of our solar system. The researchers estimate nearly 50% of all Earth's water came from this particular birthing event. And Earth likely inherited most of its water from its planetesimal phase, which is supposed to be the precursor to the planet itself. But it still does leave some unanswered questions. It doesn't explain how all the water reached the Earth, but the study shows that understanding the amount of heavy water we have on this Earth is the first step in figuring it out. Water lies at the center of it all. So next time you're drinking some water, know that this water may have once been floating around as a vapor cloud, or if you want to be a bit more closer to home, a T-Rex may have drunk this.